Apologies for the rough start. Good morning, everyone. My name is Seth Patello. These are my colleagues, Maxwell Tyree and Ethan Ribb. Together, we comprise Team PEC. Our capstone project this year is a fiber optic annunciator. An annunciator is a centralized warning panel that is comprised of many LEDs that will illuminate when there is a problem with the system. The main motivation behind our project is electromagnetic interferences. These interferences can cause false positive on traditional annunciator systems, causing unnecessary downtime and maintenance, which is time-consuming and costly. As you can see by this diagram, EMI is entering a traditional annunciator and our annunciator. It is causing the alarm to go off on the traditional annunciator, while on ours it is not, which is good. Our anticipated best outcome is a working prototype with equivalent functionality to traditional annunciators, while it remains immune to electromagnetic interferences. Our prototype will feature 12 continuity checks, meaning it is capable of monitoring 12 system inputs. As you can see by this diagram, our board will monitor a breaker that will be in a PEC power cabinet. It will take in 12 channels into the input board and then communicate their status over to our annunciator board, where their valid or invalid state will be displayed on the LED panel. Upon achieving our best anticipated outcome, we have many implications and economic impacts on the power distribution industry. Currently, we are striving to make our entire project for under a price point of $600, which we are achieving at roughly $510. As you can see, many annunciator systems are in the range of $700 to over $3,000. Additionally, there are no fiber optic annunciators currently on the market, so we have a niche in that sense. Along with greatly reduced costs, we will increase the reliability in power substations by reducing the occurrence of false positives due to our use of fiber optics rather than copper wire. We will also increase grid safety by reducing the need for on-site visitation to potentially dangerous power substations. I'll now pass the presentation off to Maxwell, who will discuss our technical accomplishments.
All right. So our overall strategy for this project was to start with known, reliable hardware. This way we can prove that our system is fully functioning before it is implemented in custom hardware. So for this, we've chosen an FPGA module, a Xilinx Arctic 7, and an associated carrier board from Trends. You can see these here, the FPGA module and our carrier board. Most notably, the carrier board features an SFP cage, which will allow us to use like an SFP transceiver for our fiber optics. Our main goal for this semester was to prove out data transfer over fiber. This proved to be the most challenging task just due to the complexity of the IP we're using and our overall unfamiliarity with the hardware at the start of the project. So we started by implementing the Aurora IP reference design. Aurora is just a Xilinx IP that allows us to use the gigabit transceivers on our FPGAs. So we spent a lot of time troubleshooting this project. We spent a lot of time just simply troubleshooting it just with a simple loopback, which just sends the data from one side of the FPGA right back to itself. And eventually, we were able to get this working. We did this, eventually got this to work between two different FPGAs, and then further modified the reference design to send custom data over fiber. Meanwhile, we also built out the other key feature of our design, which is the continuity check module. Our continuity check module will monitor the continuity of 12 circuit breakers, and it does this by simply outputting a signal to the breaker, and then just checking the received signal on the other side, and then using this information to come to a decision as to whether the continuity of that breaker was valid or invalid. These breakers are usually normally open or normally closed, so additionally, our module is configurable as such. Our major technical accomplishment this semester was a completed functional prototype of all of the components that we have working so far. So what you can see here, we have our breakers, which are just wires on our breadboard. These are being monitored by the input board, which is performing continuity checks periodically. Then the state of each of these breakers is being sent down through the fiber to the annunciator board, where that state is being displayed on this LED panel here. As you can see, the green LEDs will indicate valid continuity and everything is working. And then the red will indicate invalid, meaning someone like a technician should go out and service that breaker. With this, we're very, very close to achieving our anticipated best outcome. And actually, we'll have this demo at our panel, so please feel free to come check it out. But there are many other features that we want to add to this, and I'm actually going to hand it over to Ethan Ribb to talk about those.
Okay, so some of the future goals that we have in mind are to implement a test button and an acknowledge button. In the picture, that's just an Annunciator that's on the market, which will be very similar to ours. As you can see, it has the acknowledge button and the test button on the bottom. Ours will have 3 buttons, but the test button in our system will run a simulation of continuity checks over fiber and then display the result on the front LED panels. The acknowledgement button is so that a technician can silence any alarms so that they can go in and restore continuity on any given channel. We have also started working on serial port communication, which will allow that technician to go out and just plug in directly to the front of the Annunciator board via USB and configure each channel as normally open or normally closed, as well as the delay time. The delay time is just from when a channel goes invalid to when the alarm actually goes off. So as you can see, they'll just come out to the site with a laptop. The configuration data will go to the Annunciator board via USB and then over fiber to the input board where that will be updated. Some more goals that we have in mind to do next semester are a reset button, which will just be a full system reset. As you can see here, while the continuity check is running, it will just monitor the reset button. If it's pressed, it will clear the continuity on every channel, whether it's valid or invalid, and restart the continuity check. We would also like to research and choose DC to DC converter modules that will allow us to step down from a high voltage, whatever's available at the substation, to power our boards at a lower voltage. We'd also like to finalize schematic capture, and we've been adding things to schematics all along as we prove them out and finalize them. So we'd like to have that done before the end of next semester so that PCB fabrication can begin. This is a finalized version of our functional block diagram. In the orange are our anticipated best outcome items that we're very close to completing. Surrounding that are the items that we're still working on, including the DC to DC converters up above and the buttons that will be connected to the Annunciator board. And then at the bottom here, you can see fiber going from our boards to this big block here. That will be the client, which could be miles away, just so they can have a copy of the Annunciator at their site wherever they are, just for convenience, and so they can check continuity there. And with that, we'd like to thank everyone that's helped us this semester. So thank you.